Often the word super is used as a prefix in mathematics, and a lot of times this is like really confusing. What exactly do we mean by using super as a prefix? Well, it turns out that that answer depends on exactly what type of object we're talking about. So I thought I'd make a video today where I shed a little bit of light on this idea of using super as a prefix in the world of algebra. And so in particular, we're going to look at the notion of a superalgebra. So before we look at that notion of a superalgebra, let's look at the notion of an algebra in general. So an algebra is a vector space over some field. We'll use the complex numbers, although it won't really matter, together with a multiplication operation satisfying some rules. So we will not assume that this is a commutative algebra or an associative algebra. We'll keep it as general as possible, which means we're only left with three conditions that this must satisfy. One is a distributive rule from the left. So A times quantity B plus C is the same thing as AB plus AC. And then A plus B quantity times C is AC plus BC. Furthermore, we want the scalar multiplication of the vector space to be well behaved with this multiplication of the algebra. And so we've got this rule down here. So if we've got a constant alpha in our field, I've called it K, but again, we could think just complex numbers or real numbers, then the scalar multiplication of alpha times A times B is the same thing as alpha AB, which is the same thing as A times alpha B. Okay, so before we do the definition of a superalgebra and some examples, let's just look at some examples of algebras. So maybe a very classic example would be the algebra of n by n matrices with entries in C, where our operation is just matrix multiplication. So let's notice that this is associative. Matrix multiplication is well known to be associative, but this is non-commutative. Again, in a first linear algebra course, you learn about the matrix multiplication not being commutative. Okay, so what about another example? Maybe we could do something like polynomials with entries or with coefficients in the complex number. So these are polynomials in a single variable. So let's note that this is associative, but it's also commutative. So this is associative and commutative. And that's because if you multiply two polynomials, it doesn't matter what order you multiply those polynomials in. Another example that we saw in a recent video would be something like the three-dimensional complex vector space and then the cross product. And this is non-associative and non-commutative. So I'll just write that, non-associative and non-commutative. This actually is something called a Lie algebra, which we won't really talk about so much in this video. We'll mostly be worried about associative algebras and superalgebras. So maybe let's do one more example before we jump into the definition of a superalgebra, and that's called the Grassmann algebra. And we saw this in a much earlier video where we looked at the exterior product of vector spaces, but we won't review that. And so the Grassmann algebra, maybe with four variables, it's kind of like not super interesting until you get to about four variables. So I'll call those variables theta 1, theta 2, theta 3, and theta 4 satisfies the following rules. So we have theta m times theta n is equal to minus theta m n times theta m. In other words, we've got this like anti-commutativity. If you switch the order, you pick up a minus sign. But notice this implies that theta 1 squared is equal to 0, and similarly theta 2 squared is equal to 0, and so on and so forth. And why is that? Well, notice if m is equal to n, then we get theta m squared is equal to negative theta m squared. But if we're outside of a field of characteristic 2, that means you've got some object is equal to its negative, and the only time you can ever have that is for that object to be equal to 0. Okay, so this guy right here can be thought of as being related to this guy up here. Here we've got a commuting variable, whereas down here we have non-commuting variables. They're actually anti-commuting variables because we pick up this minus sign. So this would be another example of an associative and non-commutative algebra. Okay, so now that we've got some examples of algebras, let's maybe look at the definition of a superalgebra. Now we're ready to look at the definition of a superalgebra. So to start with, a superalgebra is an algebra itself. So in other words, it's got some sort of product satisfying those rules that we looked at on the last board. But as a vector space, it can be decomposed into the direct sum of two parts. So we generally write it as A, so that's our algebra, is equal to A0 direct sum A1, where we think about A0 as being the even part and A1 as being the odd part. And so this is actually like a microcosm of what most of the time happens with super mathematical objects. So generally, super mathematical objects can always be decomposed into even and odd parts. That's kind of like the big idea here. Okay, so anyway, back to the definition. You might say, well, what is there left to talk about? And that is, well, how does this multiplication work together with this even and odd decomposition? And that actually rounds out the definition of a superalgebra. So if A is in the mth component, so it's either even or odd, and B is in the nth component, so it's either even or odd, then A times B is in the m plus nth component, where we're thinking about this addition occurring mod 2. So I should point out that it's not required for any element of the algebra to be solely contained in the even space or the odd space. But since we've got this direct sum, you can always think about the even part of a vector and the odd part of a vector. Okay, so anyway, this is like a nice, quick chart to think about how this multiplication is really working. So if you take two even elements and you multiply them, you get an even element. An even element and an odd element gives you an odd element. An odd element times an even element also gives you an odd element. And then finally, the product of two odd elements gives you an even element. Okay, so now let's look at some examples, starting with our nice example we saw on the last board, which was the polynomial algebra C adjoin X. So let's recall that that was associative and commutative. So we need to break this into an even part and an odd part so that this kind of stuff is satisfied. And there's actually two canonical ways to break this into those parts. So the first way would be just to say that C adjoin X is the even part, and then the odd part is just the zero vector space. And I won't say too much about this, but in fact, if you have an algebra, you can kind of trivially think about it as a superalgebra just by considering the whole of that vector space to be the even part. So this is not super interesting. Okay, so what's our second way? Well, the second way will be to split this into even and odd polynomials. So let's say that's our second way. So we'll say A0 equals even polynomials. So that would be like the polynomial ring C adjoin X squared. So that gives us all even polynomials. And then A1, those will be all odd polynomials. So that would be like X times the polynomial algebra C adjoin X squared. So that gives us an odd polynomial, an arbitrary odd polynomial. And since we've got two descriptions of this algebra as a superalgebra, that really shows us that the description of an algebra as a superalgebra is not unique, although there is a canonical description. I would say in this setup, the canonical description is actually this one up here, even though it's maybe less interesting. And we'll see that a little bit later, but it's based off of the fact that calling an odd polynomial an odd object is a little bit like unnatural in terms of like the bigger idea of superalgebras or superstructures in general. Okay, so let's maybe look at some examples of this multiplication rule working. So notice that something like x plus x cubed is an odd polynomial, so that's an A1. And then something like x squared plus 3, that's an even polynomial, so that's an A0. So now let's take x plus x cubed, that odd element, and multiply it into that even element, x squared plus 3, and just make sure we get an odd element. So this is just straightforward polynomial multiplication. We get x cubed times x squared, which is x to the 5th. We get x squared times x, which is x cubed, plus another 3x cubed, so that'll be plus 4x cubed. And then finally we have 3 times x, so that'll be plus 3x. The important thing to note here is every exponent here is odd, meaning that we are in the odd space. Now let's take this x plus x cubed term and multiply it by maybe itself. We could multiply it by another odd polynomial, but just to keep it simple, let's multiply it by itself. So x times x cubed times x plus x cubed, I should say. So that's going to be x to the 6th plus 2x to the 4th plus x squared when we multiply everything out. But check it out, it's pretty easy to see here that all of the exponents are even, which means we have an element from the even subalgebra. So we took 2 odd elements, we multiplied them together, and we got an even element. Okay, so this is a nice first example of a superalgebra, but let's look at something a little bit more interesting. So for our next example, which is a little bit more interesting, is that Grossman algebra, or that exterior algebra with 4 variables. So again, we'll call that A. And we need to compose this into even and odd parts first. Let's recall that these variables anti-commute. So if you multiply them in one order, you get something, but if you multiply them in the other order, you get the negative value. Okay, so anyway, so the even components will be defined as follows. So I'll just give them by the basis. So it'll be the span of the number 1. So remember, 1 can be thought of as a polynomial with anti-commuting variables. It's just only got constant part. And then theta 1, theta 2, and then theta 1, theta 3, theta 1, theta 4. So those are all of the quadratic elements that include theta 1. And then we'll also have like theta 2, theta 3, theta 2, theta 4, finally theta 3, theta 4, and to finish it all off, theta 1, theta 2, theta 3, theta 4. So that degree 4 object. You might say, well, is there anything higher than degree 4? And there is not. And that's because if you were to try to get something with a degree that is higher than 4, one of these variables would be repeated. But if one of those variables is repeated, then you get 0 because theta 1 squared is 0, theta 2 squared is 0, etc. by our earlier conversation. Okay, so this is the even part. Now let's look at the odd part. So that's going to be the span of, well, it's going to be everything that looks like a odd variable here. So that'll be like theta 1, theta 2, theta 3, theta 4, and then theta 1, theta 2, theta 3, theta 1, theta 2, theta 4, and then let's see, theta 2, no, maybe theta 1, theta 3, theta 4, theta 2, theta 3, theta 4. So those are everything in the odd space. And now let's just check with a couple of examples that combining 2 even things gives us an even thing, and then so on and so forth. So let's maybe take 3 theta 1 theta 2 plus theta 2 theta 3. So that's most definitely an even object here. And then let's multiply that into maybe theta 1 theta 3 plus theta 1 theta 4. And then plus maybe 5. Okay, so we've definitely got two even objects. Let's see what happens if we multiply those together. So to start off, if we do 3 theta 1, theta 2, so let's maybe underline these in green, we'll color code. So doing that product right there gives us 0. So why does that give us 0? Because it gives us a repeated theta 1 object, but we know that theta 1 squared is 0. So if we were to maybe do this in the margin up here, just for this first example, we would have 3 theta 1 theta 2 times theta 1 theta 3. But that'll be negative 3 theta 1 squared theta 2 theta 3. So the minus sign comes from moving this theta 1 past this theta 2. But then we know that theta 1 squared is equal to 0, making this whole thing 0. Okay, nice. Next, likewise, we see that 3 theta 1 theta 2 multiplied into this term right here, theta 1 theta 4, is also 0 for the same sort of reason. So the only way we don't get 0 multiplying this first term is to multiply it by 5. So here we'll have 5 times 3, so that'll be 15 theta 1 theta 2. Okay, so now we need to multiply with this second term. So multiplying this second term into this first term right here again gives us the number 0 because we've got a repeated theta 3. And then multiplying it into the next one will give us something like this, plus theta 2, theta 3, theta 1, theta 4. And then multiplying into the last term gives us plus 5, theta 2, theta 3. Okay, so that would be like one way of writing the product of these two polynomials and anti-commuting variables. But let's notice that this middle term can be rewritten a little bit, and we probably like to rewrite it so it looks like it comes from one of these basis elements. So we've got something that's degree 4 here. Maybe we can reorder it so it looks like theta 1, 2, 3, 4. And we can easily do that by taking this theta 1 and commuting it past theta 3 and theta 2. We pick up a minus sign each time. So we pick up a minus sign moving past theta 3 because of the anti-commuting that we saw before. We pick up another minus sign moving past theta 2 because of the anti-commuting we saw before. So those two minus signs cancel and leave us with theta 1 times theta 2 times theta 3 times theta 4. Okay, so now that we've seen a sample calculation in this space, let's maybe look at one more thing before we're done. We're going to look at the notion of commutativity versus supercommutativity. Okay, so we're going to finish off with the notion of commutativity versus supercommutativity. So let's say we've got a superalgebra A. So we say that superalgebra is commutative if for all A and B in A times B is the same thing as B times A. So let's maybe look at a quick example of something that is commutative. Well, that would be like C adjoin X is commutative. So we know that because if you multiply any two polynomials, you can do it in any order. And this is commutative regardless of the way you think of it as a superalgebra, based off of our two ways of thinking of this as a superalgebra. Whereas C adjoined theta 1, theta 2, theta 3, theta 4 is not commutative. And that is just quickly because, for instance, theta 1 times theta 2 is equal to negative theta 2 times theta 1. So those are not the same. Okay. So on the other hand, we say that a superalgebra is supercommutative if for all A from the mth component and B from the nth component, A times B is equal to negative 1 to the m times n, B times A. So in this case, we've got our Grassmann algebra. This is supercommutative. So we might ask ourselves, well, why is that the case? Well, we're not going to work out all of the details, but let's note that, for example, theta 1 and theta 2 are both inside of A1. They're both odd components. And then we have theta 1 times theta 2 is the same thing as negative 1 to the first power times theta 2 times theta 1, kind of as necessary. Then let's work through another example. So let's maybe look at theta 1 times theta 2 and theta 3 times theta 4. So those are both even elements. And then if we do theta 1 times theta 2 times theta 3 times theta 4, that's going to be the same thing as negative 1 to the 0, theta 3, theta 4, theta 1, theta 2. In other words, these two pairs of elements commute. And this is not immediately clear, but if you just count how many times you have to slide one past the other, you'll see that it works out. So as this theta 1 slides past theta 4 and then again past theta 3, you pick up a minus sign twice. But then after doing that, you can slide this theta 2 past theta 4 and theta 3 and pick up two more minus signs. So in the end, you've picked up minus 1 to the fourth power, giving you plus 1, which is the same thing as minus 1 to the 0. So it works out in this case as well. And then maybe to convince yourselves that everything's okay, check that theta 1, this odd component, this odd element, and theta 2 times theta 4, which is an even element, commute with each other, which is exactly what should happen because 1 times 0 is equal to 0. So I'll leave that for you guys to check. Okay, so this was just a brief entry into how super can be used as a prefix in mathematics based off of the idea of a superalgebra. Well, there's also other super notions in mathematics like Lie superalgebras, or there's a whole subject of supergeometry. There are things called supermanifolds. There's a notion of a supergroup and so on and so forth. But these all boil down to this idea of being able to split something into even and odd parts. And that's a good place to stop.